Hi everybody, my name is Professor Rad, and today we're going to talk about rational and irrational numbers. So let's get started. Now, as a reminder, we've been talking about several different kinds of numbers throughout this course. We began with natural numbers and whole numbers. So natural numbers are the numbers you start naturally counting when you're young, so 1, 2, 3, 4, 5, and so on. The whole numbers are the same as the naturals, but they toss 0 in as well. The integers are the same as the whole numbers, but then they toss in the negatives. And the real numbers are any number that's a decimal. So like 5.6 or negative 2.8. In this list, each of the subsequent types of numbers includes all the previous ones. So for example, if I have a number that's an integer, it is also a real number because real numbers include the integers. If I have a number that's natural, that means it is also a whole number and an integer and a real number. So today we're going to split up those decimal numbers. All the numbers that we've got so far, I think of them as kind of like building them up from like the ground up. These are kind of whole number values. So now let's take a look at some numbers that are not whole numbers that are still different in important ways. So, a rational number is any real number, any decimal number, that can be written as a ratio of integers. Basically, any number that you can write as a fraction. So for example, 2/5 or 9/7 or 1/3 or 6. 6 is a rational number because we could write it as 6/1. So any number that can be written in fraction format, where the top and bottom are integers, are going to be rationals. And in fact, any negative versions of these as well. If we think about what these numbers look like in decimal format, they're going to be decimals that either terminate or repeat. So for example, I'm going to see what these look like in decimal format. So on this calculator, it has a button down at the bottom, and we'll talk about this in future videos as well, but it can change fractions into decimal format using this button here. So if I enter in that fraction 2/5, and then I press that button, it converts it into 0.4. 0.4 is an example of a terminating decimal. It means after the 4, it ends, it terminates. Now, secretly, there's a bunch of unnecessary zeros that can be written, but if it ends in a bunch of unnecessary zeros, we're going to say it terminates. All right, let's think about negative 9/7. Okay, now this one is a repeating decimal. It starts out with a negative 1.285714, and then it starts to repeat. So the 2 repeats, and then the 8, and then here it's showing me a 6, because what the calculator is doing is it's taking the 5 and rounding it up because of the 7. So the 285714 is going to be the repeating component to this decimal. So that's an example of a repeating decimal. So anytime you can write a number as a fraction of whole numbers, or negative numbers, a fraction of integers, you'll get either a decimal that ends or one that repeats. If you have a number that doesn't do that, in other words, it's a decimal that doesn't repeat and it doesn't end, then we say it is irrational. So an irrational number is a decimal that cannot be written as a fraction. So an example of that would be something like, usually some good examples that they give are pi. So you might have heard of pi before. It's about 3.14. If I find pi on my calculator, this calculator has a pi button right here. It will turn into a few more digits, so we can see it's going on, and I don't see any pattern to these digits. Now, one of the unfortunate things about repeating numbers with calculators is that the calculator screen ends, but pi doesn't. And so I don't know if maybe somewhere out over here, if we continued writing the digits, if it would repeat or not. Okay, I kind of have to take it on faith that pi doesn't repeat. Now, mathematicians have done proofs and things like that to show it doesn't repeat, but that's beyond the scope of our class. Another common example that's given as an irrational number is the square root of 2. So if I find the square root of 2 on my calculator and write it out in decimal form, I see again that there's not a pattern here that's repeating. Now, notice that some digits repeat, like 4 happens a couple times and 2 happens a couple times, as does 1, but I don't have the same sequence, right? I have 4, 1, and then 4, 2, 1, and then 3, 5, 6, 2, totally different. But the reason I don't really like pi and the square root of 2 as examples for irrational numbers is because, like I said, I can't tell from this that it's never gonna, just suddenly start repeating. So I'm gonna give you an example of an irrational number that we can tell for sure is never gonna repeat. How about this number? So let's say I've got 1 point. Let's go with a 2, 1, and then 2, 2, 1, 2, 2, 2, 1, 2, 2, 2, 2, 1, and so on. So this number, the decimal component does have a pattern to it. So the pattern is I've got a single 2 followed by a 1. Then I have 2 2s followed by a 1. Then I have 3 2s, a 1, 4 2s, a 1, and then we'll have 5 2s followed by a 1, 6 2s followed by a 1, and so on. So irrational numbers can have patterns to them, but this pattern is never going to come all the way back to the beginning with just a single 2 and then a 1, and then 2 2s and a 1. Because the number of 2s can just keep growing forever. It never has to come back to just a single 2. So although there's a pattern here, this pattern's never going to come back and repeat itself in the way that the 285714 comes back to repeat itself. So this is what I like as an example for irrational numbers. So if we visualize all of the different number types that we've talked about now, this is what it can look like. So this big box is our real numbers box. All of the numbers other than real numbers that we've talked about up to this point are rational. So natural numbers, whole numbers, and integers are all types of rational numbers. And again, that's because you can take any whole number, whether it's a positive or a negative, and throw it over 1. So you can write it in fraction format. Irrational numbers are all the other kinds of decimals that either don't end or don't repeat. So let's do a few examples of identifying whether numbers are rational or irrational. Okay, so I have 6 numbers that we're going to look at for this example, and we're going to decide whether it's rational or irrational. So 3/5. 3/5 we can write as a ratio of fractions, so that means it's rational. By the way, they didn't, pick rational and irrational because it is sane or not sane, like irrational, kind of like crazy, right? Ratio is hiding out here in the word. So a rational number is ratio null. You can write it like a ratio. And irrational is irratio null. It's not able to be written as a ratio. So, and remember, a ratio is what we were calling fractions before we called them fractions. So 3/5 is rational. 0.54 is also rational. I know that 54 hundredths is rational because it's a decimal that ends. So nothing happens after the 4, so that makes it a rational number. 8. Remember that any whole number is also a rational number because we can think of it as 8/1. So there it is, a fraction of integers. So this one is also rational. Now we've got a negative number. So both rationals and irrationals can be negative. So don't let the negative throw you here. Instead, what I'm noticing is this bar over the 7. So what that means is that this decimal is negative 0.2 and then just repeating 7s forever. So this decimal is a repeating decimal instead of terminating because the 7 is going to just continue to repeat. Rational numbers are decimals that either terminate or repeat. So since this one repeats, this is also rational. All right, now for part E. Okay, so we've got 1 0 1 0 0 1 0 0 0 1 0 0 0 0 1 and so on. So what's the pattern? So this ... means that it's continuing in a pattern of some kind. So that's why I was asking what the pattern is. And the pattern looks like we're having an increasing number of zeros between the ones each time. So there's a pattern, but this pattern doesn't repeat. It's kind of like the 1s and 2s that we looked at before. So because this pattern doesn't repeat, that makes this one an irrational number. And when I say repeat, just a reminder, I'm not talking about digits repeating. I'm talking about like the complete sequence of digits. So you can have more zeros and more ones, but what happens is I'm never going to cycle back to 1 0 1 again. Okay, there's always going to be more than 1 0 in between the ones going on. And for this last one, we've got 0.333 ... So this is the same as if I had 0.3 with a line over it, or because I happen to know them, this type of fraction, this is 1/3. So 0.3 repeating is a repeating decimal, so that makes it rational. Okay. Now, just sort of as like an extra credit for these. Oh golly, didn't mean to hit the screen there. Just wanted to zoom out a little. So kind of as an extra credit, we can look at the other types of numbers that each of these satisfy. So 3/5 is rational and it's also real. All of the numbers that we look at in this course are real numbers. In an algebra course, you might learn about numbers that are called complex. Those are not real numbers, but all of the numbers we're going to look at are real. 3/5 is not an integer because if I change this into decimal format, for example, I don't get a whole number back. 54 hundredths is a real number. And again, it's not going to be natural or whole or an integer because it's got values after the decimal point. However, 8 is a natural number and a whole number and an integer and a real number. So it's real because all these numbers are real. And then it's a natural number and a whole number and an integer because it's a whole amount, 8, right? It's a counting number. So since it's a counting number, it satisfies all of them. Negative 0.27 repeating. Immediately, because it's 0 point something, we know it's not natural, whole, or an integer. So this one is rational and it's also real. This irrational number, every irrational number is also real, but it's not any of the other kinds we talked about. And then for part F, we've got this nice decimal going on, so that means it's real. But this one again is not natural, whole, or an integer because it's got this decimal component. All right, so I've got a now you try problem here where you can try to identify what types of numbers these numbers are. You really just want to focus on rational versus irrational, but if you want to go for the extra credit like I did in the last example, you can go ahead and also classify them as real or natural or whole or integer as well. In the next video, we are going to talk about how we can change from one form into another. So I think the next video is about how to go from a fraction form into decimal form. And then in the video after that, we'll go backwards. We'll go from decimal form into fraction form. So I hope you found this video helpful, and I'm looking forward to seeing you next time. Bye for now, everybody.